In the previous video, we computed the moment of inertia of a right triangular slab by slicing it into thin rods that were perpendicular to the rotation axis. In other words, the way we have our slab oriented in this picture, we did it by slicing into horizontal rods. Now in this video, we're going to compute the moment of inertia by slicing it into thin vertical rods that are parallel to the rotation axis. So we're streamlining things a bit this time, and I already have a picture of a representative thin vertical slice that's parallel to the rotation axis here. And we gave that a mass of dm, a width of dx, and we called the height y. Now we call the horizontal location of these slices x, and as x varies, we see that y varies. As the position of a slice goes further to the right, it's going to get shorter. Now, before we start doing a moment of inertia calculation, there's just a quick reminder up here of the definition of area density. We normally give that a lowercase sigma, and that's the mass per unit area. In other words, it would have units of kilograms per square meter. That's going to be a handy way to phrase everything in this problem. And notice that we can turn around that relationship to say that mass is sigma times A, or area density times area. So we're going to use both of these relationships at different points in the calculation. So to get things started, what we need to do is write down the moment of inertia contribution of this thin vertical slice. So we're going to call that dI. And because 100% of the mass in that slice is at exactly the same distance from the rotation axis, in other words, the distance of x, we just get the same thing as the point mass moment of inertia. In other words, mr squared, or in this case, dm times x squared. Again, anytime you see 100% of the mass exactly the same distance from the rotation axis, it's going to have a moment of inertia just like a point mass. And we've seen this before with a thin ring, and we've seen it with a thin cylindrical shell. Well, this time it's just a vertical slice that happens to be all located at a distance of x from the rotation axis. So the next step here is to express dm using this area density idea. So I'm going to call that sigma times dA, where dA is the infinitesimal area of that thin slice. Well, that's not too hard to write in terms of x and y. That little rectangle dA has a height of y and a width of dx. So now we have the expression sigma times y dx times x squared for this moment of inertia contribution. And the practical problem with this is that we have two different variables in that expression. We have x and y. We need to phrase this entirely in terms of a single variable if we want to integrate it. So here's where we have to write down the relationship between y and x. Remember, as x changes, y is changing. The height of those thin slices is changing. And the equation that describes that relationship between x and y is just the equation of this line that's actually the hypotenuse of our right triangle. So we're just thinking about slope-intercept form here, and I can write this as y equals slope times x. Well, slope is rise over run, and that's negative h over b. So negative h over b times x plus y-intercept, so plus h. Now we can replace y in our expression for the moment of inertia contribution, and then we'll be ready to integrate. So making that replacement, I have sigma, and I'm going to go ahead and pull an h out as I'm going. So sigma times h, negative x over b plus 1 times x squared dx, just moving the dx to the end this time. So now we're set up with an expression for the moment of inertia contribution of this single little slice, and we can add them all up by using an integral. So I'm going to start by saying I, the total moment of inertia, is the sum of all the moment of inertia contributions. This is what an integral does. It's a summation device for summing up infinitely many infinitesimal contributions. And now we can write our expression for dI, the moment of inertia of one of those infinitesimal contributions. And we're adding all these up as x goes from 0 to b so that we can cover this entire slab in vertical slices. So our limits of integration are 0 to b. So our constants, of course, are spectators here. So I'm going to write sigma times h. And then we'll go ahead and distribute this x squared to both of the terms in parentheses to make it easier to see how to use the power rule in this integral. So in my first term, I'll just go ahead and separate the constant. I have negative 1 over b times x cubed. And in my second term, I have just an x squared. And then we have our dx at the end there. Now each of those terms is integrated by the power rule. So x cubed integrates to 1/4 x to the 4th. So our first term then is a negative 1 over 4b x to the 4th. And our second term integrates to 1/3 x cubed. And now we're evaluating this from 0 to b. When we sub in the lower limit, we get 0 because each of those terms vanishes. When we sub in the upper limit, in the first term, we end up with a b to the 4th, and one of those b's is going to cancel, leaving us with a negative 1/4 b cubed. And then in our second term, we have a plus 1/3 b cubed. So the b cubed can be factored out, and then the common denominator there between negative 1/4 and plus 1/3 is 12. So I have 4/12 positive and 3/12 negative. So I end up with just a 1/12. And if I smash everything together here, I have sigma h b cubed over 12. So there's one final thing that has to be done here. The way this problem was given to us was with the dimensions of the right triangular slab and the total mass. So we want to write sigma in terms of those. So sigma is total mass divided by total area. So that's going to be m over 1/2 base times height, which we could also write as 2m over base times height. And we sub that into our expression for the total moment of inertia of the slab, and I end up with a 2m over 12bh times hb cubed. So now the h's are going to cancel. One of the b's cancels, leaving me with a b squared in the numerator, and a 2 cancels, leaving me with a 6 in the denominator. And we arrive at our final expression for the moment of inertia. That's 1/6 mb squared, and that agrees with our previous result, so we're happy. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the ZachSlab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.